Hello, this is Jifeng Sun from Colorado State University. Here I'm going to share with you my research titled Versatile and Controllable Shape Morphing using Twisted and Coiled Actuators. First, I will introduce the motivation of this research, and then introduce the artificial muscle that we used to actuate our shape morphing, and how can we use this actuator to generate the versatile programmed motion, and how can we control it to realize shape morphing. First, a motivation. From the top two fingers, which are the pioneer works in this research field. The first one is a robotic skin that can turn any object, any soft object, into a robot. And the second is a liquid crystal elastomer with liquid metal inclusion. When the temperature increases, it can morph into a complicated shape and hold that shape. So when I say shape morphing, here our schematic is to use artificial muscle and embed it into a soft body to generate different kinds of motion. And we use variable stiffness element to hold the final configuration. And for variable stiffness element, we mean an element that can change its stiffness. That means if I want to be soft, it's soft, and if I want to be rigid, it's rigid. So it will allow the robot to change it into its desired configuration and hold that configuration. So first, we'll introduce our artificial muscle, which is called Twisted-and-coiled actuator. For short, we call it TCA. It's an artificial muscle, which is low cost, has large energy density, 100 times stronger than human muscle. You can see in this video, it can generate 50% of the stroke. And it has self-sensing capability, which is shown in the second video. When the TCA contracts, the resistance change with respect to the displacement it can generate. And then by sensing the resistance, we can infer the displacement and control that displacement using a closed loop PID control. And then we can hold a position. And the benefit of this control is that it can reject environmental disturbance. For example, if I blow air into it, the TCA can still hold that length, even though, the displacement drops a little bit, but then with the closed loop control, it will be able to find its target position and hold that position. And the good benefit is that this sensing capability is available even when it's not actuated. That means when it's not actuated, I stretch it, the resistance will change. By sensing that resistance, we can know if there's any stimuli or not, which can be used as a signal to trigger some motions. That means the TCA knows the environmental change. For example, if I push the TCA or pull the TCA knows that I'm pulling it, which is, we call it innovated smart actuator. Also, by embedding this TCA into a soft body, we can generate all kinds of different motions. For example, we can generate bending motion by embedding it into this circle shape. We can build a gripper to grip different kinds of things. And also, we can generate bending motion. For example, if we embed it in a parallel shape, we can generate 3D bending. And this bending motion can also be controlled. We call it innovated soft robots. First, In the beginning of this video, I just manually turn it, bend it, and the TCA knows that I'm turning it, I'm bending it, and then it starts to work and hold that configuration. And also we can generate all other different kinds of motions, for example twisting. And by combining those three different motions, we can build a robotics arm that had three parts. First, it has a bending manipulator, and then a twisting manipulator, and a gripper at the end. This robotics arm can first rotate its gripper and grip something, lift it, and bend its arm to replace this object into this cup. After different kinds of motions are generated, we can combine a variable stiffness element with those robots to generate a shape morphing robots. And those shape morphing robots will have the capability to achieve all kinds of different configuration and hold that configuration. And the variable stiffness element we used in this structure is called laminar jamming. And the basic working principle is several layers of paper are put in a plastic pouch. When the air is sucked out of the pouch, the structure becomes rigid. And when the air pressure is released, it becomes rigid, it becomes soft. Combining this laminar jamming structure with a bending manipulator, we can build a variable stiffness gripper. And this gripper will first actuated by this TCA to generate a bending motion, and once the configuration is reached, the laminar jamming structure will become rigid to hold that configuration. And the benefit is that after the laminar jamming structure is actuated, the TCA don't have to work anymore. And potentially we can hold that configuration without any energy input. Also, more complicated shape morphing is shown in the second video. In this surface, we can embed TCA on different locations. When the different combination of TCAs are actuated, this surface can morph into different shape and hold that shape using the laminar jamming structure. Conclusion. First, in this research, we have present artificial muscle that can enable better soft robots because it's faster, it generates larger stroke, it has the capability to do self-sensing. And the soft robots actuated by this artificial muscle can generate first and programmable motion. And also using the sensing capability of the actuator, we can control the motion. Combining those soft robots with a variable stiffness element, we can build a shape morphing robot with morphing and holding capability. And the more complicated shape morphing can be achieved by embedding as many TCAs as you want and control them individually. And potentially, we can build a very, very complicated soft robots and shape morphing robots. Okay, thank you so much for listening.